All right, welcome back. We are continuing to look at prior independent approximation. And in particular, we're going to be looking at uh, one of the main approaches to driving revenue in optimal auctions, which is reserve pricing, posting the monopoly price. And we're going to compare that with something uh, that's going to be typically worse, but not too much worse, which is posting random prices. And in particular, random prices from the same distribution that the values are drawn from. Okay, so we're going to warm up with a simple uh, uh, result for pricing to a single agent. Okay, so remember the definition of the monopoly price. We're going to be writing things in quantile space, and so we'll say Q hat star is the monopoly price, and this is the quantile that maximizes the revenue curve. Okay, so we're going to be looking at showing an approximation result. So we're going to let ref of f be the revenue from posting the optimal price to a single agent. And we're going to let APX be the revenue from posting a random price drawn from the distribution to the agent with value from that distribution. Okay, the theorem that we're going to show is that if this distribution is regular, then our approximation mechanism is a two approximation. It gets at least half of the revenue from posting the optimal price. Okay, of course, uh, this is implied already by the Below-Klemperer theorem. And why is that? Well, to see this, note that the revenue of the second price auction with two agents. Well, each agent faces a price that's the other agent's value. That's a random price. And so the revenue of the two agent second price auction, which is the efficient auction for two agents, is equal to 2 times APX. Okay, and um, and so uh, and what do we know from the Below-Klemperer theorem? We know that uh, this uh, revenue of the second price auction is at least uh, the optimal revenue. So we know that this is at least the optimal revenue with one agent, and that's exactly equal to our ref here. Right, it's the optimal revenue from one agent. Okay, and so um, dividing both sides by 2, we see that APX is at least half of ref. Okay, um, I like giving this proof because it's a very simple geometric argument, uh, and that gives a lot of intuition for why uh, it's a simple geometric argument that gives a lot of intuition and immediately suggest generalizations, which we'll be turning to next. Okay, great. Okay, so I want to start out by looking at what this reference mechanism is. And so let's draw our revenue curve. Okay, so this is our revenue curve, R of Q. Okay, and what is our reference mechanism? It says find the Q hat star that optimizes this curve. And that's going to be R of Q hat star. Okay, but this axis here goes from 0 to 1. And so an equivalent way to write R of Q hat star is 1 times R of Q hat star, which is in fact the area of a rectangle. It's the area of this rectangle containing, or the rectangle that the revenue curve is inscribed inside of. Okay. Great. All right. What about our approximation mechanism? So our approximation mechanism posts a random quantile. Okay, so what is its revenue? Well, its revenue is going to be the expectation of a random quantile being posted. And the revenue we get from that is exactly equal to R of Q hat if we post the random quantile Q hat, with Q hat drawn uniformly from 0, 1. And so writing that out as an integral, that's just the integral of R of Q hat dQ hat, in particular because, again, Q hat is drawn from the uniform distribution because quantiles are always uniformly distributed. Okay, and that is, of course, the area underneath the curve. Okay, so this is APX. Okay, this is ref. Great, well now we're basically done. So now observe that the rectangle is at least the area of the revenue curve because it's the revenue curve is described in the rectangle. But now observe that because of regularity, in other words, because of concavity of the revenue curve, the a triangle can be inscribed inside the revenue curve. The triangle going from 0, 0 to the monopoly price and then to 1, 0. And so that triangle by concavity is inscribed inside the revenue curve. Okay, and so the revenue curve is at least the area of that triangle. But of course, the area of that triangle is exactly half the rectangle. Okay, and so we see that our reference mechanism, the optimal pricing revenue, is at least our approximation mechanism, of course, because it's optimal and our approximation is an approximation, which is at least the triangle, which is exactly equal to 1/2 of our reference mechanism. Okay, great. And of course, our theorem is these last inequality. Great. So that is the simple geometric proof that the revenue from posting a random price from distribution to a single agent is at least half of the revenue of posting the optimal price. Okay, and it's easy to see that these inequalities are tight on either side. Um, this inequality could be tight if the revenue curve, in fact, looked like a box. This happens for the so-called equal revenue distribution, and this inequality can be tight for a revenue curve that looks like a triangle. Great. Okay, so that was a simple setting of a single agent and considering posting the optimal price versus posting a random price. So I now want to look at how these same ideas can be used to consider much more general environments where posting random prices is pretty good compared to posting the optimal price. Okay, so first I want to define a generalization of uh, the second price auction with reserve. Okay, so this is the efficient mechanism with a lazy reserve. So what we're first going to do is we're going to ask for bids. We'll assume these bids are values, and then we're going to find the efficient allocation. After doing so, we're going to enforce the reserve price. And then we're going to use the usual payments that we have for this allocation rule, which is monotone and therefore it's incentive compatible. Okay, so we're first finding efficient allocation, and then any of the agents that are allocated in that efficient allocation that don't meet their reserve are then discarded, and the winners have to be the ones that are both in the efficient allocation and meet their reserve. Okay, this contrasts with what's called eager reserve prices, where I first remove all the agents that don't meet their reserve, and then I try to find the efficient allocation constrained to the agents that are remaining having met their reserve. Uh, okay, so this is the lazy efficient mechanism with lazy reserves. Great. So I said I want to get beyond a single agent, and I want to also get beyond a single item. I'm going to look at matroid environments. Matroid environments have been covered already in previous classes. Uh, uh, a matroid environment is one where the feasible winners are the independent set of a matroid. Uh, there are some notable matroids for auctions. The most relevant one is called the transversal matroid. This matroid corresponds to matchings, and matchings come up in all kinds of auction and market design questions. If you aren't familiar with matroids, I welcome you to just think of a multi-unit auction, which is also a matroid. It's the uniform matroid. But think of a multi-unit auction. So imagine I have n bidders and k items for sale, k identical items for sale. And so any subset of size K is feasible. Any subset of size bigger than K is infeasible. Okay, the first thing I want to do is ask, suppose we had just purely an algorithmic question. How would we uh, optimize? Okay, and so here's a very natural algorithm that's sometimes good. And in fact, in this case, it's good. So it's the greedy by value algorithm. What we do is we sort the values in decreasing order, and then I iterate over these values in this decreasing order. And if it's feasible to serve the next agent with the value, then I select that agent to be served. Otherwise, I discard the agent and reject them. Okay? And after going through all the values and adding all the ones that I can, note that I might not be able to add a value if it's infeasible given the constraints that and the previously selected agents. Okay, so after I run through each value, then I'm going to output the selected values as the winners. Okay, so looking at what this does for the K unit auction is actually kind of boring because we sort the agents in decreasing order, and what do is we just select the top K agents. Those are the ones that I can add them because it's still feasible. But after I've selected K agents, the K plus first agent I can't add because it's infeasible, and all subsequent agents I can't add because it's infeasible. But this it's sort of a trivial algorithm for the K uniform matroid. For other matroids, like the transversal matroid, it's actually an interesting algorithm. Okay. And the theorem is that the optimality of this algorithm actually characterizes matroids. Okay, so a set system is a matroid if and only if greedy by value is sufficient for every set of values you can have. Okay, you can find the proof of this in chapter 4 of the textbook. I'm not going to go into the details. Great. So here is a simple consequence of this theorem about optimality greedy by value. If I have IID regularly distributed agents and a matroid environment, then the efficient mechanism with monopoly reserves is the optimal mechanism. Okay, I'm going to leave this as an exercise that I encourage you to figure out on your own before watching the next video. Okay. The next theorem is again the same environment, IID regular matroids. If I replace the monopoly reserve with a random reserve drawn from the same IID distribution, then the efficient mechanism with this random reserve is with a lazy random reserve is a 2 approximation. Okay, and we will do this as an exercise in class. All right, that concludes this session on monopoly versus random reserves.